So hello YouTube, welcome to the Wednesday lecture on September the 16th, that should be, yes it is. And we're talking about our covalent molecules, showing those chemical bonds as the atoms come together and now share electrons to complete their octets. We're talking about elements which have a very closely matched ability to attract electrons. So the electrons are shared instead of stolen, as we saw in ion chemistry. And so we said we could draw these Lewis structures, draw these covalent molecules by following 5 rules. We said step 1 was just counting the valence electrons. Step 2 was choosing a central atom. Step 3 was getting the skeleton down, that basic framework, by connecting everybody to the central atom. Step 4 was starting to fill the octets with the electrons that we had left. And then 5, if we ran out of electrons but still had incomplete shells, then we could reimagine and redistribute those lone pair electrons as bonding pairs, but only if we still needed to complete the octets. So let's take a look at silicate, SiO3 2-. It's one of the polyatomic ions, but not one of the polyatomic ions we had looked at in chapter 3. This is a different one. So as we count the electrons, let's pull up a periodic table, because you'd always have a periodic table given to you in an exam. Okay, and so as we look at silicon, there is silicon there. So it's the 1, 2, 3, 4th box in the row. It has 4 boxes in its shell for each oxygen. It's 1, 2, 3, 4, 5, 6, the 6th box in the row. So 6 electrons in its shell. Remember, as we count boxes, we're counting electrons. Oh, there's some late additions for us to join our merry band. So for that silicate, we get 4 and then 6 times 3, which gives us 22. And then there's the electrical charge itself on the ion, which is telling us we've got 2 more electrons than we expect to have. And so our total is 24. 4 for silicon, 6 for each oxygen, and then the electrical charge itself, telling us about a surplus of electrons in this polyatomic ion. So 24 total. Choosing the central atom, it's the element which needs the most electrons to complete its shell. So silicon needs another 1, 2, 3, 4, and would be expected to form 4 chemical bonds. Oxygen needs another 1, 2 to complete its shell. So we normally expect 2 chemical bonds. Now the elements sometimes break these rules, but it's a good guideline to get us started. And so with silicon needing more electrons, expected to form more chemical bonds, that's our choice for the central atom. We connect it to the surrounding oxygens, and that gives us our framework, our skeleton. And that used 2, 4, 6 bonding pairs of electrons drawn as a line each time. So that takes us down to 18. We use those remaining 18 electrons to fill octets, but we'll start with the outer atoms, the 3 oxygen atoms. So 6, 12, 18 electrons, and we've exhausted our supply before we get to the silicon. So for the silicon, because it only sees 2, 4, 6, we can go to our 5th rule and use a lone pair from one of the oxygens and turn it into a bonding pair. So just randomly, we'll choose the oxygen here in the top left, take away that lone pair, turn it into a bonding pair. Oh, beg your pardon. And turn it into a double bond between the oxygen and the silicon. Now we know we're finished because we have the octets. 8 electrons for each oxygen, 8 electrons for the silicon, and we can show that. So for our double bonded oxygen, look at its 360 degrees circumference. We've got 1, 2, 3, 4, and then the bonding pairs, 6, 8 electrons around it. Same with the single bonded oxygens, looking 360 degrees around it. 2 electrons in the bonds, so 2, 4, 6, 8, an octet as well. And then the silicon itself, again looking 360 degrees around it, 2, 4, 6, 8 electrons. So a complete octet. That's the state we're trying to get to because that's the noble gas state when the shell is complete. So although they're taking a different tactic compared to ion chemistry, it's still the same goal because it's still the same laws of chemistry, the same thing to make them stable, a completed shell of electrons. If we look at sulfur tetrafluoride, it'll introduce us to the idea of hypervalency. So SF4, sulfur tetrafluoride, 6 electrons for a sulfur atom, just straight off the periodic table. 1, 2, 3, 4, 5, 6 for sulfur. Each of the fluorine atoms, as we count its position in the row, 7th element, 7 electrons. So 6 for sulfur, 7 for each of the fluorine atoms. That gives us a grand total of 34. We'll choose sulfur as the central element because compared to fluorine, sulfur needs 1, 2 electrons, and therefore would expect it to make at least 2 bonds, while fluorine only needs 1 more to look like neon. So we normally expect 1 chemical bond for a fluorine atom. So sulfur should make more chemical bonds. So we connect it to the fluorine atoms. It actually makes 4. That's okay. Again, they do sometimes break that rule of thumb for the combining power, the number of bonds we expect, but it did lead us to the correct answer for the central atom. And so the sulfur bonded to the 4 fluorines that used 2 electrons each time. So we have used 8 of our 34 electrons, leaving us with 36. And we use those remaining electrons to start filling octets, starting on the outside and only putting electrons in the sulfur if there's nowhere else for the electrons to go. And so we fill those octets for the fluorine atoms, and we do have a pair of electrons left. So that lone pair has to go in the sulfur itself. This looks like a problem because now the sulfur is breaking the octet rule. We look at the environment around it. We see 2, 4, 6, 8 in the lone pair, 10 electrons. This isn't supposed to happen. Well, sulfur, along with a couple of other elements we'll look at, are what we call hypervalent. They can stack additional electrons into the outer shell because they are elements in the third row. They are elements which have 3 shells and therefore have access to a D subshell. Of course, that normally gets filled later, but compared to the 3p, the 3d is very close in energy. So these hypervalent elements break the octet rule and add more electrons into the 3d subshell. So again, we see that the D subshell, when it first appears, really is part of the third shell. So there's only 3 elements that we'll look at which can pull this trick. And they're right next door to each other in the periodic table. Phosphorus, sulfur, and chlorine. Phosphorus, sulfur, and chlorine. These are what we're going to refer to as hypervalent elements in the third row. They can break the octet rule. Now, phosphorus sometimes has 8, as it should, but sometimes it sneaks 2 electrons into its D subshell to give it a total of 10. Sulfur can have 8, or sneak in 2, like phosphorus, to be 10, but it takes that a step further and could be as many as 12 electrons to complete its shell. Again, using orbitals in that d subshell. Chlorine, on the other hand, one step further than phosphorus or sulfur. It can be 8, it can be 10, it can be 12, or even 14 electrons. So that potentially creates a problem. Which of these answers is going to be the correct answer? 8 or 10 for phosphorus, 8, 10, or 12 for sulfur, or 8, 10, 12, or 14 for chlorine? Well, I'm glad you asked, because that's exactly what we're going to talk about next. With these hypervalent elements, when they're at the center of a molecule, we will use that hypervalency to get rid of any formal charge on the hypervalent element. So when we get rid of the charge, we've got the right combination. What is formal charge, you ask? Well, I'm glad you asked that too. Because the elements are sharing electrons to complete their shell, but sometimes their share is a little bit more than we expect, which would make it negatively charged, rather like an ion. Or maybe it has an insufficient share of electrons, which should make it positively charged. And we can check on formal charge to see if there is positive or negative charge on each of the atoms. So we've basically got two kinds of electrons around the atom to make up the octet, because we've got those lone pair electrons. These are electrons which are not involved in chemical bonds. So they belong specifically to that one atom. The lone pair in red belonging to the nitrogen, the lone pairs in green on the left belonging to the oxygen on the left, the lone pairs in black on the right belonging to the oxygen on the right. These are electrons which are counted towards that particular atom, and they don't form part of the count for other atoms because they're not part of a chemical bond. Because the other kinds of electrons are the bonding electrons. These are the electrons shared between two atoms of nitrogen in a molecule, 2, 4, 6 electrons with that triple bond, but they are shared electrons in mutual space. So as we look at the shell of the nitrogen on the left, like that, and the shell of the nitrogen on the right, like that, you can see the lone pairs are not involved in chemical bonds. They're not being shared, but those bonding pairs have to be divided between the two atoms sharing, like splitting up a pie with a sibling if you're going to share a pie. And it's an equal share, one electron from each bond to each of the two atoms in the bond. So that gives us an electron count for each atom from its octet. We count all of the lone pair electrons, but we only count half of the bonding electrons. So for the nitrogen here, there's 2 lone pair electrons and 6 bonding electrons, but we'll only take half of those. So of the 8 electrons around it, 5 of those electrons belong to the nitrogen. Similarly, with the examples we had above on the screen, I clear my space here. Look at the nitrogen and the oxygens, and I guess also the silicon. Get my drawing package, there we go. So we're talking about the nitrogen. Because it has an octet, it has 8, but it's got 2 lone pair electrons which belong to it, and half of those 6 bonding electrons. So also coming out with an answer of 5. That's kind of what we expect because, of course, nitrogen is the 5th element in that period, and it needs to borrow another 3 to make up its octet, so that makes sense. The oxygen on the left, it's got 1, 2, 3, 4 lone pair electrons. And then there's the bonding electrons, another 4, but it only has ownership of half of those electrons, giving us a total of 6 from 8. So we have to be careful here. Be clear between how many electrons the element sees in total to complete its octet, which is normally going to be 8, and distinguish that from how many of those electrons actually belong to that specific atom. We look at the silicon next door, and I'm going to clean up my picture a little bit. Let's get rid of that there, and get rid of that text up there. And we'll talk about the silicon. Let's use a different color just to be fancy. So for the silicon, there's its shell, all the electrons around it. It doesn't have any lone pair electrons, but it does have 8 bonding electrons. And we're going to take half of those. And so we get an answer of 4. 4 of the 8 electrons around silicon actually belong to it. It has ownership of those electrons. And again, that's the answer what we expected, for the silicon, because it's the 4th element in the 3rd row of the table. And it's borrowing another 4, 2 from each of those oxygens either side, to make up its octet. So that's the first part of this for formal charge. Just understanding how many electrons actually belong to that atom. Second half is, what does the periodic table tell us to expect for that atom? So if we look at the examples here in silicate again, there's the periodic table count compared to the Lewis structure count, which we've just been doing. And so for the silicon itself, because silicon, the periodic table tells us, should have a count of 4 because it's the 4th element in the period. So it should control 4. But as we look at the structure, it's 1 electron from each of those bonds. It is actually 4. So 4 minus 4, 0 formal charge on the silicon. However, with the oxygens, we're going to get some different answers. Let's take the double bonded oxygen first. Again, what does the periodic table tell us? What do we expect it to be? Well, the periodic table tells us, oops, I pulled up the wrong thing there. Periodic table tells us to expect 1, 2, 3, 4, 5, 6, because it's the 6th element in the row. How many electrons does the double bonded oxygen actually control? 1, 2, 3, 4, and then 1 from each bond, 6. So 6 from the table count, 6 from the Lewis structure count. It's electrically neutral too. But if we look at those single bonded oxygens, we're going to get a different answer. Again, how many electrons should the oxygen atom control? That's just straight off the periodic table, as we've already looked. 1, 2, 3, 4, 5, 6. How many does it control? Again, as we look at it, looking at that shell around the oxygen, 1, 2, 3, 4, 5, 6 electrons, and they belong exclusively to that oxygen. And then 1 of the 2 bonding electrons. So the count is 7. So that periodic table position told us 6, but it's actually 7 of the 8. And so there's a -1 charge on that single bonded oxygen. Same with the other oxygen in the top right corner. Same environment, it will be the same answer. So we can update our picture of silicate by showing the formal charge when it appears. -1 and -1. That explains the 2- charge on the silicate ion when we first introduced it. The individual charges become the sum of its parts. So we can use formal charge checks like this to see whether the hypervalent elements stick with 8 or go up to 10 or 12 if you're sulfur or chlorine, or 14 exclusively if you're a chlorine atom. Remember, as we said earlier, for the hypervalency of those 3 elements, the only ones we'll look at, they could all be 8. I didn't realize it was that far back. But phosphorus takes that step further sometimes and is 10. Sulfur takes that step further sometimes and can be as many as 12. And chlorine can take it a step even further and be as many as 14. And we'll use the hypervalency in a Lewis structure to get rid of formal charge on the hypervalent atoms themselves. So they're the only examples we'll look at where there's a breaking of the octet rule. Any questions at this point? We doing okay? So we're normally looking for octets. But when we have a hypervalent element at the center of the molecule, check for formal charge and see whether you're going to use that hypervalency of the element. You'll know when to stop adding electrons to the hypervalent element because you'll get a neutral atom. Okay, let's take a kind of 5-minute break or so. And while you're on the break, just take a look at these structures and work out the formal charge for each of the atoms in this molecule. Remember, it's a comparison of the periodic table position for the element compared to the electron count in the Lewis structure. This is the number one thing that trips people up in chapter 4. Be clear between the total number of electrons the element can see as it's looking for an octet, and then just the electrons which belong to that atom as we're counting for formal charge. Take a couple of minutes and then we'll come back to this. Okay, and I will pause the video. Don't let me forget to unpause. Okay, we're back from our break. Let's just make sure that took and it's recording. Yes. So we're looking for the formal charge of each element as it's shown in the Lewis structures. So of course carbon, when we look at the periodic table, it's the 4th element in that row. So it should control 4, but it controls 1, 2, and then 1 of the 2 in each bond, a 3rd, a 4th, a 5th. So there's a formal charge of -1 on the carbon, which you can put in the top right-hand corner, as we would do for an ion. With oxygen, it's the 6th element in the 2nd row of the table. So if it's neutral, it should control 6 electrons, but it actually controls 1, 2, 3, 4, 5, just half the bonding electrons. And so we've got a formal charge of +1 for the oxygen. Moving over to the next molecule, the sulfur trioxide. That double bonded oxygen, of course, it should be 6, as we said previously. And it is 6, 1, 2, 3, 4, and 1 of the 2 in each bond. So electrically neutral. And if it's a neutral atom, we don't normally bother putting anything in. We only put in a value if it's electrically charged. For the single bonded oxygens, again, it should be 6 because that's its position in the periodic table, but it actually controls 1, 2, 3, 4, 5, 6, 7 of the 8 electrons around it, formally giving it a charge of -1. Oxygen below, the same environment, the same number of bonding electrons and lone pair electrons, so it's the same answer for the same element. Likewise, anytime you see oxygen with 2 lone pairs and 2 bonds, it's always electrically neutral. For our 3rd molecule here, because hydrogen is the 1st element in the 1st row, and it does control 1 of the 2 electrons, giving it a duet, like helium, so no charge on any of the hydrogens. The oxygen, double bonded like its neighbour up above, should control 6 and does control 6, so electrically neutral. The phosphorus is the fifth element in the third row, but it only controls 1, 2, 3, 4 of the 2, 4, 6, 8 electrons around it. So again, be clear, between the electrons it sees to fill its shell, that octet, counting all the electrons around it, and then checking for formal charge, and just checking the electrons which specifically belong to it, one in each bond. So a +1 charge on the phosphorus, and the sulfur, like oxygen, should control 6 because it's the sixth element in the third row of the table, but it's actually controlling 7, one more than it should, so a -1 charge on the sulfur. Any questions about those ones or anything else related? We're doing okay? Again, that's one of the big catches for the chapter. Be clear between how many electrons it needs for its octet when you're initially drawing the Lewis structure, but then there's a distinction to calculating formal charge and how many electrons just belong to that particular atom. Let's try drawing another Lewis structure, but one which has a hypervalent element at the center, and so we'll have to think about formal charge. One of the polyatomic ions that we had looked at in chapter 3, phosphate. So let's see if I left a gap for this. Oh, it's actually, we've got it on the next page. So again, starting off with just the electron count based on the position in the periodic table. Of course, that's 5 electrons for phosphorus because it's the fifth element in the row, and 6 electrons for each oxygen because it's the sixth element in that row. So the 5 plus the 6 times 4, and then we've got the electrical charge on the polyatomic ion itself, 3 minus. So that 3 minus charge, that's telling us about a surplus of electrons. Things are only negatively charged when they have more electrons than protons. And so we'll add those 3 electrons to our count to give us a total of 32. We choose phosphorus as the central atom because it needs to make more bonds, because it needs more electrons. And we'll surround it with the oxygen atoms. And then we connect the central atom to the oxygens using 2 electrons at a time. So we'll use up 8, 2, 4, 6, 8 electrons, and use the remaining 24 electrons to start filling the shells, work on the outside, and work your way in. So this 24 can be used to fill the octets of the oxygens, and we run out of electrons before we get to the phosphorus. Now that might be okay because phosphorus, of course, has an octet as we've drawn it, 2, 4, 6, 8. But remember, it's hypervalent. It can go up to 10. So should we leave it at 8 or continue to 10 with a double bond? We can check formal charge to find out. So just to be thorough, we'll check the formal charge of the oxygens around it. From the periodic table, it's a 6th element, so it should control 6 of the 8 electrons around it. But it controls the 6 lone pair electrons and one of the 2 bonding electrons, giving us 7. So 6 minus 7, as we saw with the other examples of a single bonded oxygen, there's a charge of -1. That's a -1 charge on all 4 of those oxygens. Looking at the phosphorus itself in the center, of course from the table it should be 5 electrons because it's the 5th element, but it actually controls, as we look at the bonds, just 1, 2, 3, 4, coming up 1 short and a charge of 1 plus. So this does not look like a happy molecule at all with all this formal charge on the molecule. We know we can use the hypervalency of phosphorus, And we want to use it to try and get rid of that +1 charge. So let's take a lone pair of electrons on the top there, and we'll convert it into a double bond, and let's see what that does to formal charge. So I'll have to just write this in here. Let's switch to red, give red some love. So for the oxygen at the top, of course, it should control 6, but now it controls 1, 2, 3, 4, 5, 6 instead of 7. That's why that formal charge has disappeared. The phosphorus, of course, in the third row should control 5 because it's the fifth element, and it does control 1, 2, 3, 4, 5 of the 10 electrons around it. 2, 4, 6, 8, 10. We said that's allowed for phosphorus because it's hypervalent. It's putting a pair of electrons into one of its d subshell orbitals. Phosphorus gets away with this, and it makes it an electrically neutral atom. You always know when you're finished a Lewis structure with a hypervalent central atom because you've gotten rid of the formal charge normally. Any questions about that one? Too quiet in this class, way too polite. You can be rowdy, you can say, "Oi, stop foreigner," or something to that effect, and ask me to go over something again. If you're having a problem with it, then I bet your last dollar that there are other people in the class having problems with it. Don't ever feel that you're on your own or that you're the only person who doesn't understand something. I see the exams every year, and that is not true. Any questions? Still being too shy? Remember, office hours every night at 9:30. Hopefully that's a nice quiet time of the night for everybody when they can regain their sanity. And just take a little bit at a time. Don't think about the enormity of what you're trying to learn, just one piece at a time, and then move on to the next piece. So let's try another one, this time perchlorate. And for this one, the central atom is going to be chlorine, even though it should really be oxygen from the way we've been talking so far because it needs more electrons. Sometimes it's the hypervalent element which actually wins and becomes a central atom. In an exam, with an example that breaks our normal thinking, which is of course the element which is more electron hungry, if we're breaking that rule, I'll tell you that we're breaking that rule, okay? So I'm telling you straight away with this one that it's chlorine, which is the central atom, not one of the oxygens. Let's see, we'll probably make this the last one for today, but take a couple of minutes and try that one, and then we will break for today. Let me see what my kids are up to. Okay, we're back after a short break, after all that cursing and swearing that Maria was doing. Right.
What?
Well, just saying, you know. So let's see, looking at this one. So somewhere, oh, dang it, there's my glasses. I keep like 5 pairs of reading glasses in the house because I keep losing them. They turn up in the bathroom or in the bread closet and things. Anyway, so looking at the perchlorate, again, that's a new ion to us. It's not one of the ones we had studied in chapter 3. Of course, looking at the position of chlorine in the table, it's the 7th element in the third row, so 7 electrons. 6 electrons for each oxygen. And then that formal charge itself telling us about 1 more electron than we'd normally expect. So we get a grand total of 32 electrons. Now normally we'd choose the element which is more greedy for electrons for our central atom, but we've been told for this one that it is actually the chlorine. Sometimes the sheer size of an atom outweighs the number of electrons it needs when it comes to chemical bonding. So chlorine at the center, we'll connect it to those 4 oxygen atoms. And that uses 2 electrons each time. So that takes us down to 24. We'll use the remaining electrons to try and complete octets, starting on the outside. So lone pairs for the oxygens as we bring them up to 8. And adding the lone pairs to the oxygens actually uses up our electron supply. 6, 12, 18, 24. Now maybe this is the right answer because of course chlorine does have an octet. It's got to be at least 8. But remember it can break its own octet rule because of that D subshell nearby. And it could be 10, it could be 12, or even 14. So which count is going to be the correct answer? We said we compare the periodic table position to the electron count in the Lewis structure, just the electrons which belong to that atom. So let's take a look. We'll do it for the oxygens as well. Oxygen should be 6, but it's actually 7 as we've drawn it right now. So there's a -1 charge on each of the oxygens. And for the chlorine, it's the 7th element in period 3. So it should control 7 electrons to be electrically neutral, but it only controls 1, 2, 3, 4, 1 from each bond. So currently there's a formal charge of 3+ on the chlorine. And we said we'd use the hypervalency until we can get rid of that formal charge for chlorine. So let's try 10. So we'll take a lone pair that we had originally drawn on one of the oxygens. Let's just take the lone pair there. And we'll reimagine that lone pair as a bonding pair instead to its neighbor chlorine. Now the oxygen here controls 1, 2, 3, 4, 5, 6 from the 8 around it. So we've gotten rid of the formal charge there. Should be good for the molecule. And the formal charge on the chlorine now, it did control 4, but now it controls 1, 2, 3, 4, 5 electrons. So the formal charge comes down to +2. So even 10 isn't working for us because we haven't gotten rid of the formal charge. Let's try 12. So we'll try taking another lone pair of electrons and turning it into a bonding pair, like this. That gets rid of the formal charge on the oxygen here because it now controls 6 electrons out of 8. 1, 2, 3, 4, and 1 from each bond, 5, 6. So the formal charge on the chlorine has also diminished. Now controlling 1, 2, 3, 4, 5, 6 of the electrons around it. That creates a charge of 1+. So 12 isn't working either. Let's try 14, our last possibility. We can't take it any further than 14. And so we'll take another lone pair, actually. I didn't want to do that. Another lone pair and turn it into a bonding pair. So now around the chlorine, It controls 1, 2, 3, 4, 5, 6, 7 electrons. There we go. That's the value we're looking for. So no formal charge on the chlorine now, and we've taken it to its maximum hypervalency. One thing to note as you are looking for the right answer, it's not just that the hypervalent element has lost its charge, but the charges left add up to the overall charge of the original polyatomic ion. So -1 overall, and we can see it's specifically just this single bonded oxygen which carries that -1 charge for the molecule. Any questions before people disappear for lunch? We're doing okay, honest. That's one of the trickier parts to the chapter, hypervalency. 3 elements all together in the third row, which can break the octet rule. Phosphorus can go up to 10, sulfur can go up to 12, and chlorine can go up to 14. You know when to stop when you get rid of the formal charge on the hypervalent atom itself. We check formal charge by comparing the periodic table position to how many electrons actually belong to that atom in our Lewis structure. Okay, thanks for keeping me company today. I know not many people seem to do that, but I appreciate the company. And I'll talk to everybody on Friday, if not earlier. Bye, guys.
Bye.
Any questions before we finish off? Are we feeling good? Feeling good? Okay.
I really
Okay,
wish
thank
that
you.
site would hurry up and get this thing fixed.
Well, just keep trying, pepper them with questions. I mean, I tried, let's see, let me switch off the recording and hang in there for a second, Harrison. See, just